I'm sure the person who posted this knew they were joking because clearly we all see God in algebra much more than we would see Satan. But it's a good reminder here that we've got some important, serious work to do with our algebra and pre-calc all the way through calculus. So know these common functions and know them well. Make sure you can do these problems without a calculator. So I'll try switching colors here, using blue to graph the blue functions and red to graph the transformation. So our basic parabola function, when we square a value, it gets larger, except when you are between -1 and +1. When you square a fraction, it actually gets smaller when you square a proper fraction. So please make sure that you always label some point so that we know the size of the units on your graph. Do not assume that you're counting by ones. All right, and then function g of x, if we're subtracting 1 from x, use your common sense instead of just memorizing transformations. In order to get 0 in this parenthesis, we would have to let x equal 1. So when we subtract from the x coordinate, we shift the graph to the right. So same graph, shifted 1 unit to the right, and we'll label the key point there. In number 2, we've got x to the 4th. Well, x to the 4th, we might say grows faster, but in fact that's only true once you're bigger than 1 or smaller than -1. So before you get to the point 1, 1, the graph is actually flatter. So think of taking 1/2. When you square 1/2, it's 1/4, but when you raise 1/2 to the 4th power, it's 1/16. So we actually get a very flat U-shaped bottom here when we do the 4th power function. And then when we subtract 1 outside the function, that's going to change our y coordinates. So we're going to shift everything down 1 unit. So exactly the same graph, a rigid transformation is what we can call this. But the blue graph slides down 1 unit. In number 3, sometimes it's easy to make mistakes on the simpler problem. So remember that this is the same as y is equal to 3, and that's our horizontal constant function. So we could think of it as y equals 0x plus 3, so it has a slope of 0. And our second function we could think of as y equals 1x plus 0. So a y-intercept at the origin and a slope of 1. So this is our 45-degree line. And pick some point here and label it so we can see the size of your graph. Absolute value function, I'm sure most students just remember that it's a V shape. Technically remember that it has a slope of +1 on the right side and a slope of -1 on the left side. And the definition would actually be a piecewise defined function. So the absolute value of x is x if x is greater than or equal to 0, but it would be the opposite of a negative number. So we'd have to do a double negative, the opposite of x if x is a negative number. So that's telling us that this part, the second quadrant part, has a slope of -1. And then we do 2 transformations. Subtracting 1 from the x, we're going to move to the right 1 unit. And then outside the absolute value, we have the opposite sign. So that's going to make everything that used to be positive negative. So a vertical reflection when we have an opposite sign outside the function. So we'll move our corner 1 point to the right and then flip it upside down. And label at least 1 point. Any point would be fine. Make sure you label something. All right, the square root function has a domain issue. We can't do the square root of a negative is not real. So the square root of x looks like one branch of a parabola. So for example, we know if we go over to 9, we're only at a height of 3. We go over to 100, we're only at a height of 10, so it's rising. This might look like we mean it to be a horizontal asymptote, but it's always rising. And of course, we have our point here of 1, 1 that appears on so many of our graphs. And on function g of x, we have an opposite sign inside, an opposite sign on the x. So now instead of choosing positive values for x, we can only choose negative. So this we would say is our horizontal reflection. So now the domain would be negative infinity to 0. So this negative sign is going to flip the graph horizontally. And then we do this negative sign outside the function. That changes the sign of the y coordinates to negative. So that's now a vertical reflection. So now as a second step, our graph would be down here. And then we have this 2, and that's a vertical shift up. You might be more familiar with seeing it back here. So that's going to take the graph and move it up 2 units. So the red graph has exactly the same shape as the blue graph, but we've done several transformations. In number 6, the cube root has no domain issue. The cube root, we'd go over to 8 to get up to a height of 2. So I might make that even lower. Maybe that looks a little too high. So over to 8 to get to a height of 2, and we have an odd function. When we go to negative 8, we have a cube root of negative 2. And of course our point 1, 1 and our point negative 1 are in the graph. So there's our cube root function. And then function g, we might rewrite this also as a cube root. The denominator of an exponent is a cube root of x squared. So this makes it an even function. So for example, we're doing the cube root of x squared, so it's going to be a little higher than it was. So we're going to have a graph that's a little bit higher. And we know it's going to be an even function, because whatever we put in for positive x, the negative value is going to give us the same thing. So this red graph, we might, this is not a math term, but we might start calling that a seagull graph. It has a very sharp corner right here, both parts. So the 2 parts would give it symmetry. So it is an even function. All right, and question 7, now we have x cubed. Well, x cubed, like a parabola, grows very quickly. If we label a point, we might choose 2, 8. And it's an odd function, so if we chose negative 2 and cube it, we would be negative 8. So this we know is an odd function with symmetry to the origin. And we've got 2 transformations. So this negative outside the function is our vertical reflection. And then we're going up 2 units. So let's turn this upside down and slide it up 2 units. So the part that was rising will be falling. The part that was falling will be rising. And we could label this key point as 0, 2. All right, let's proceed. Now we're switching. Now our variable is in the exponent, and our constant is the base. So now we're into exponential functions. And the common point that all exponentials share is when the exponent is 0. So any base to the 0 power will produce 1. So 0, 1 is a common point on exponential functions. If we let x equal 1, we would have 3 to the first power is 3. So our graph is going to rise on this side. And if we put in a value like negative 1, the negative exponent, remember, is the reciprocal. So we would be at 1/3, and then 1/9, and then 1/27. So it keeps getting smaller and smaller, but it will never be 0. So we've got an asymptote. It gets closer and closer. So exponential functions have a horizontal asymptote. And then we are adding 2 to the x coordinates. So think what you would do. You would choose your x coordinates to be 2 units smaller than they were. So it is the same shape of the graph, the same horizontal exponent, but now we would have our key point and every other point shifted 2 units to the left. All right, question 9. If you've forgotten some of your geometry, let's take this equation. Let's write it instead of function form. Let's write it as an equation, and let's square both sides. And I hope you'll never have to write this again. I hope this will be familiar to you. This is a circle with a radius of 3. So this equation is not a function. It is an entire circle. but we only want the positive root. So we only want the principal root here. So our y coordinates are only going to be the positive part of that circle. So we simply want the top semicircle. And if we label these 3 points, that will give us the idea that you know it's a circle. And question 10 is similar, but with the center transformed. So again, let me do this the long way. Change it to equation form, and then hopefully you'll do this by observation the next time. Let's move the 1 with the y. And then if we square both sides, so you'll see that we're coming up with the equation of a circle again. So now we can move this x term. And the only difference now is we still have a circle with radius of 3, but the center of the circle has shifted. So to get the 0, 0 point, we would have to choose -2 for the x coordinate, and we would have to pick +1 for the y coordinate. And, sorry, I wrote 3 there, but it's really a 9. The radius would be equal to the square root, which is 3. So our center is at -2, +1. And our radius, if it were an entire circle, would be 3. This is the equation of the entire circle. But now let's look what we've got here. We don't want the entire circle. We want a function, and we are taking the negative roots. So we're taking the negative root only, and that means we want the bottom semicircle. So if this is our center and we've got a radius of 3, we could mark off these points here. So this would be at the point 1, 1. And if we go down 3 units, that would be at -2, -2. And if we go 3 units this way, this point would be at what? -5, 1. So when it's the negative root, we want just the bottom semicircle. Hopefully this is all sounding familiar. All right, in number 11, if you compare it to what's right up above, so above we did 3 to the x. Well, e to the x is just about the same since the value of e is approximately 2.7. So the same idea, it would just be a little bit lower, but e to the 0 power would still produce 1, and we're going to get closer and closer to our horizontal asymptote on the left side. And then the natural log of x. Remember, this is the same as, sorry, I got to change colors here. Think of the definition of a logarithm. Our base is e here. So this is the same as saying e to the y power produces the x coordinate. So think what happens here if the y coordinate is 0. If the y coordinate is 0, then the x coordinate would be 1. So we're trading places here. And I think most of you remember that exponentials and logarithms are inverse functions. And do you remember that inverse functions are reflections across the 45-degree line? So our logarithmic function has a vertical asymptote. So let's label x equals 0 as our vertical asymptote. All right, question 12 is the basic hyperbola. It's the reciprocal function. So think how simple this is. You know that the reciprocal, when x is 5, the reciprocal would be 1/5. When x is 1, the reciprocal would be 1. When x is 1/5, the reciprocal flips over to be 5. So the reciprocal of a small value is large. The reciprocal of a large value is small. So most of you, now that you've done so many rational functions, would first graph your vertical asymptote. We know that x cannot be equal to 0. And when the degree of the denominator is larger than the degree of the numerator, we know that y equals 0 is our horizontal asymptote. And likewise, you could say, well, what's the reciprocal of -1/5? That would be -5. So the 2 branches of this hyperbola, I bet you don't even think too much about that anymore. Question 13 has 2 vertical asymptotes. So let's take a look at this. If you wrote it in fraction form, you can see that the two values that are thrown out of the domain, x cannot be -2 and x cannot be +2. So we've got two vertical asymptotes. And when the degrees are equal, we know that when x gets large, this -4 becomes negligible. So we know that when the degrees are equal, the horizontal asymptote is the ratio of the leading coefficients. So we know that as x gets large, we're going to have a value of 2 to 1. The numerator will be twice the denominator. So we'll label our horizontal asymptote. Our intercepts, if we let x be equal to 0, we would have 0 over -4. So 0 for x gives us 0 for y, so that is both the x and the y intercept. When is the numerator equal to 0? Obviously only when x is equal to 0. So one intercept point, and then we can start graphing. So you could try some values to convince yourself. So for example, if I put 1 in for x, you could see that we would have 2 over -3. And can you see that this is an even function? Make life easy for yourself. So if we know that 1 produced -1/3, then -1 will also produce -1/3. So I'm just going to quickly sketch the graph here. And then think, for example, if we choose a number like 3, you could actually plug 3 in there and we would have 18 over 5. So we can see it's positive. So lots of ways to think about this. And if we know that the graph is even, then it has to have symmetry to the y-axis. So cut your work in half. All right, and one more. Question 14, you might not have done much with this or seen this in pre-calc, but if you think about what happens when you pick some values of x, clearly if we picked -3, we would have trouble. If we picked -3, we would get 0 over 0. So we cannot, that's our domain, we have to have a hole in the graph there. But if we choose a number like -2 and plug it in, do you see that we would have the absolute value of 1 over 1? And if we choose a value like -1, we would have the absolute value of 2 over 2, and that's also 1. And as soon as we get to the other side here, think about putting -4 in here, we would have the absolute value of -1 compared to -1. So now we flip-flop, and all of these values would give us -1. So you will quickly remember this function even if you've never seen it before. When we are bigger than -3, the values will be +1. And when we are less than -3, the values will be -1. And we have holes in the graph here, and we'd have to jump from one branch to the other. So we will say that this has a jump discontinuity. So there's a term you'll want to remember. And that's enough.